He's a professor at the University of Fire, and he's done a lot of fundamental work in verification, in automata, in concurrency, a lot of basic work in analysis of weak memory models, various other models. And today he's going to tell us about Canonical structure.
Thank you very much. Thank you for the introduction.
Thanks for the invitation. So I'm going to present you some work which is actually relatively recent. So it's about the problem of verifying the correctness of libraries of concurrent objects, concurrent data structures. So what's the problem? For instance, when you use concurrent data structures, so the user, so you have a number of clients, like here, this T1, Tn, for instance, they use, let's say here in this example, it's a stack where you do operations like push and pop, and you want to check whether the structure is empty. So you do them at some level of abstraction, and then there is the implementation, which is invisible from the users, which is going to use some low-level representation and try to implement these operations as fast as possible. Good. So there are now two views. Well, of course, from the point of view of the user, you want to see everything as atomic, and also that these operations are somehow can be, the sequence of operations can be seen as interleaving of these atomic operations. Well, but from the point of view of the implementation, so that's another story, right? So the client want to see sequences like that, and want to reason about this kind of sequences, whereas the implementer should avoid to implement these operations really in an atomic way. So he needs to allow as much as possible that these operations will overlap in time. So the real execution will look like something like that. But still, of course, the job of the implementer is to go fast and try to maximize parallelism, but still, ensure to the user this atomic view. Okay, so that's the essential problem. So, and conceptually, this means that you want to ensure this observational refinement. What does it mean? It means that if I have a specification or some reference implementation of my library, so I want now to have an implementation which satisfies the following, is the fact that for every context where I can use this library, so if I use now my implementation, I will see precisely the same things. I cannot distinguish these things, okay, from outside, all right? So this implementation can be faster, can have better properties, for instance, in terms of performance, but in terms of consistency, it has to show precisely the same interface. Is it clear? Okay. So that's observational refinement. That's what we want to ensure. So how to do that? So there is an approach which is based on checking linearizability, because you see here the problem, there is a universal quantification here. If you want to verify this observational refinement, you want to check that, that the behavior of the client in parallel with the implementation is included in the behavior of the same client with the specification, but this is for every client, okay? So now, linearizability somehow allow you to get rid of this universal quantification. So this is a concept that has been introduced a long time ago already, and it says the following. So if I take my execution of the implementation, where you see that operations are overlapping in time, so I should be able to explain it using a sequential computation. So how I should do that? So I have to choose a point in time in each of these intervals of executions of these operations, and this is called the linearization point. And such that now, if I consider that the whole execution of this operation happens precisely at that point, Now I get some sequence now, and this sequence should be valid with respect to the specification that I have for this data structure, okay? So this means that if I take now this execution and I look at the events which correspond to calls and returns, so I should be able to reorder them, but I should respect something, which is the order between returns and calls, which means that if a method returns before another one starts, so I should preserve this, okay? But I can reorder everything else. So if I can do that, I should be able to find a sequential execution now, which is valid. And actually, it has been proved. So this, may, I think, well, it was all the time, I think, a kind of folklore knowledge, but it was proved formally that linearizability implies observational refinement, and actually quite recently by a group of authors, Filipovich, Noam Rinadsky, and I think Peter O'Hearn also. Okay, so this means that now, for instance, we can use linearizability to check observational refinement. Okay, but now, what about complexity? Is it easy? Well, so now you see, even if we are in a very simple case, where, for instance, we fix the number of threads, and we consider that our specification and regular and everything, so that problem is actually quite hard. So actually, Rajiv and others have proved in the 96 that this problem is in X space. And for the lower bound, well, it was known that it's p-space hard because at least reachability is, can be, I mean, you should at least solve the reachability. But so recently, Jad Hamza, who is one of the people who are working on this in Paris. By the way, I think I forgot to say that this is a joint work with Jad and Constantin Enea in Paris, and also Mike Amy from EMDA, who was before in Paris before he joined EMDA. So, right, so now we know that this problem anyway is X-space complete. Okay, so this means that this is a hard problem. And now actually, even if you are interested only in checking for a single computation, whether it's linearizable or not, so this is an NP-complete problem. Okay, so this means that you have some, you know, some barriers, complexity barriers there. Now, if you go to a more general framework, if you assume that, okay, now I have an unbounded number of threads, because you know, I have an unbounded number of clients trying to access to my data structure. So what will happen? Well, we show that linearizability is undecidable in that case. So you may say, well, you have an unbounded number of threads. Well, it's not that surprising that it's undecidable. Actually, it's not that straightforward. For instance, in the same paper, we have proved that serializability is decidable even if you have an unbounded number of threads. And also, now, if you consider another concept of linearizability, which is actually stronger than the usual linearizability, so this is what we call static linearizability, and it means that this linearization point that you have to choose in your computation, now you fix them in the code of your methods, all right? So if you do that, and in fact, it's quite okay for many implementations, because usually you look at the place where you commit some data, and this is the linearization point. So in that case, the problem becomes decidable. And the reason is that in that case, you can reduce this linearization problem to a state reachability problem in some model called vector addition systems, which is equivalent to Petri nets. Yeah.
Depend at least a little bit on what is the underlying data structure, because that seems like another source of unboundedness.
Sure.
Arrays and
Yes.
sorry.
So here I only have an unbounded number of threads, but still the data structure is bounded.
Okay.
But I'm saying here for this decidability business, yeah. So, I mean, before it was everything is bounded. Here, we relax, the number of threads, but still, the specification is bounded. So,
so in that case, even for, in general, it will be indecidable, and you get decidability in this case. But this is an interesting question because, this reduction, actually you can do it whatever the data type and so on. So you can have a reduction to some counter systems. And now if the data structure is unbounded, you will have arrays of integers. So you can always do this kind of semantic reductions regardless of the decidability. But now if you want to have decidability, then you have to bound so that you get to this model. Okay? So still, the result, this is okay, this is a decidability result. But again, well, as I said, what is interesting is this reduction, because once you do this reduction, now you may use whatever else method for proving, analyzing, debugging, whatever this model that you have. The complexity is still high in theory here, because this kind of models are, in general, it will be space complete. So the question now that we considered recently is to say, okay, we have all this complexity, high complexity. Let's try to find something which is more efficient, but we reduce our ambition. We don't want to prove correctness. We want to check the existence, whether there is a bug. There are bugs, okay? So this is bug detection. So what we want to find is an efficient method for detecting observational refinement violation. And the question that we ask ourselves is are the following. So we want some kind of under-approximation schema that allows you to choose, to under-approximate the set of behaviors that you have to examine, to look at. But this schema has to be parameterized in the sense that you can increase the precision if you want. Of course, we want also that this schema leads to some tractable refinement checking method. And also it has to be efficient in terms of coverage. It has to be able to find most of the bugs with small bounds and low complexity. Okay, so that's the objective. So in what I will explain to you is how do we achieve these things. So, and this goes through several steps. First, so we have to change our view. Since we are interested in observational refinement, we should not really or necessarily look at linearizability. First, let's understand this observational refinement, how we can characterize it. And what we have done is that we have provided another characterization of this observational refinement, which is precise in terms of what we call is history inclusion problem. So I will, of course, explain. And we prove that this observational refinement is equivalent to that problem. And linearizability actually is a stronger concept. And it's only equivalent in some case that I will also explain. So once we understand this, actually, in order to get this result, we have to understand some properties of what we call histories. So those are some abstractions of the executions. And from there, we derive a concept for bounding, which is called interval length bounding. And we show that this concept can be implemented in an efficient way, in the sense that we can find good representations for these histories using counters. And then we can reduce this observational refinement to a reachability problem using counters. So again, of course, it will be indecidable in general, but if you bound this, if you take this interval length bounding, then you have a finite number of counters. And in that case, again, we can show that you can do efficiently monitoring, can have a dynamic approach for checking violations, or you could also have an approach which is static. Okay, so you can build somehow some program on which you can solve the reachability problem using tools like Coral or things like that can solve reachability problems in these things. And what is interesting also is that we show that experimentally you have small bounds for detecting most of the bugs. And also it's a scalable approach with respect to what exists. If you apply the standard linearization monitoring, for instance, where you are going to check all the possible linearizability, so this approach will explode very quickly, whereas our approach will be more scalable. Right, so this is the menu, okay. So I will start now to introduce these notions of, well, first, we need to introduce some terminology somehow. So we have a set of methods. For the moment, we don't require that they are finite. There is a set of methods and a set of actions that programs can do. And they can also call these methods. So you have calls and returns events, actions. So what is an execution is simply a sequence of such actions. So you can have actions of the program, which are internal, or he can call the library and get some return value. All right? So a program then is a set of such executions, and the library is a set of executions, but over only calls and returns. So the library has this interface, and you see only call and returns. All right? Now, what does it mean that two libraries, L1 and L2, so you have this relation, L1 refines L2, if for every P program, set of this form, when you compose P with L1, all right, on the calls and returns, and you project, you remove all the internal actions of P, and you do the same from the other side, then you have an inclusion between these two sets, okay? So that's the formal definition. Now, so what is a history? Now, if I take an execution, all right? So in this execution, remember I have call and returns, right? And an operation, as I said, but maybe it was too quick, is a pair which correspond to a call and return which are matching, all right? So this is the execution of an operation, right? Now, we are going to take these operations as objects and order them using some causality order. What is the causality order? Is this one, is that an operation is considered before another one if the return of O1 is before the call of O2 in our execution, all right? So you take your execution and you extract this information, you get a history. Okay, now the objects are the operations. Good. Now, here is the important observation, is that these histories are not any kind of partial orders, okay? No, this is the history.
Just any.
Yeah. So you look, you have several threads, all right? This is your program. And you have several threads calling this library. Right. Now you take an execution is simply a sequence of, okay, call, maybe there is another call, then return, whatever, and so on and so on, okay? Now, you see you may have intervals that overlap, and those are different operations that execute in the same time, But now, what you take is that, okay, if two are like this, they are incomparable in respect to this order. So they are just 2 points. But now, if there are two like this, then you put this restriction down, okay? So now, The important thing is that since we are reasoning about shared memory, in fact, you can prove that every execution of the libraries that we are interested in, they are a special kind of order called interval orders. What is an interval order is what is shown there. Whenever you have 4 events, O1, so this is O1, is smaller than O1 prime, and if you have O2 is smaller than O2 prime, so then necessarily you have either this picture or that picture. Necessarily you will have either this guy is smaller than that one or that one. So why? You see here, for instance, this is to understand why this is true. Assume that this is, 2 threads, okay? So, for instance, and this one has, let's say, this operation, which is before this one, and so on. So you have actually two cases. You cannot have more. So, so you see, in all cases, you can say that you see this operation terminate before this one start, and you have to draw this, or you have this. And this is because really we are on a shared memory, and there is some kind of unique real time, which linearize all the events somehow in time. And now, this is an interesting observation because from there you can derive a lot of informations about the structure of your problem. So, I mean, I'm not going to give you all the technical details that they are in the paper that I will give you the reference of it, but the important here thing is that we prove, for instance, that precisely you have the observational refinement is equivalent to history inclusion. So it gives you the precise characterization. Now for linearizability, actually they are equivalent when you assume that this library is atomic. What does it mean, atomic? It means it's like each operation start by doing, okay, the whole stuff is atomic, okay? So this is the case where you consider, specifications. Usually you consider that the specifications are atomic, okay? In that case, so you have precisely observational refinement equal to linearizability. But now, if you start now, take this new library, which is not atomic anymore, and you want to refine it again, then you need history inclusion and not linearizability, okay? So that's a first. Now, in fact, also to prove this result, you need also a concept which is also interesting, is the concept of how to weaken or to abstract a history. So history is a partial order. Now you can say, okay, I define an order between histories, H1 is less than H2 if H1 has less constraints, okay, has less edges, fine? And you can prove that you have this interesting property, is that if I take a library, the set of histories of a library is downward closed with respect to that order, in the sense that, if it contains H2, it will also contain H1. So if you can, let's say, linearize H2 with respect to this library, you can linearize something which requires less constraints, okay? So actually, when you think about it, it's something natural. But this is also the key for defining our, so it plays a important role in this characterization. I mean, it enters in the proof, but also it has an important role because it will help us now to reason about approximations. Because since we weaken, you see here, so you know that if this guy is there, then the weaker one is also there. So this means that if it's not there, the other one will not be there, okay? I mean, we'll see this. So if you take, So what we are going to define is a schema of this form. What we want to define, yes, sorry, go ahead.
I'm sorry.
Yes.
Go back. There's something that popped.
Yeah. Mm-hmm.
Diagram where
Yeah.
you either have the edge from X to Y or the edge from the other.
Right. Yeah.
So this and
Well,
that's the intuition I'm getting from this.
Okay. Yeah, yeah, yeah. Let's see. Right. So, okay. Let's, okay, because, yeah, so I'm somehow mixing the histories and interval orders. So when I am talking here, I am talking about, executions and histories that you get from, these executions and from libraries. Now, I mean, here, we are talking now about, let's say, you look at these histories as orders now, and you weaken them. So initially, they are interval orders, but then when you weaken them, you will get, actually what we are going to get is, are also interval orders, which are weaker. Well, okay, I mean, here, let's take that those are two, I mean, this is not precise. Oh, okay. Not precise. I mean, the real thing is this one is that if I take two histories, okay, and this one is here, then the other one is also here. So those are I mean, they are already histories or interval orders. But I agree that if you take the whole downward closure, but everything will not be in interval order. But whenever you take, a valid history and it's less than the other one, it will be also in the history set, okay? Okay, good. Now, what we are going to do is to define some schema based on some functions that are going to deliver a history which is weaker than the original one. Right, so you have to remove something and respect the fact that it's a history. And what we want is, of course, natural requirement is that this schema is is more and more precise, and everything is less precise than H. And you can capture H if you want with this schema. And also what is important is that, checking that one of this approximation is in the history of some library should be also done in a polynomial time. Right, so that's the objective, okay? So, why this is interesting? Because what we are going to do is to choose parameters, and we are going to ask, well, we are going to enumerate, let's say, the histories of the first library, and check whether they are not in the other one. Because if they are not, then you know that the original history is not, okay? So if the approximation is not in the library L2, then the original history is not there, and you found a violation. Well, if, it's only one direction, of course, right? So, okay. Now the whole question is, how do we define this A? So now we have to dig a bit deeper on these properties of these interval orders. Actually, those concepts exist since a time ago. So here there are some technical points. So what is interesting with this interval order is that you see the fact that you all the time add these edges makes now that in some sense you can define some linear order between what is called the past. So if you look at a point, in this order, you define what is the past of this point, which is all the objects which are before. Okay, so that's the past. Now, if you look at the sets, these sets, you can order them totally. You cannot have two completely non-comparable because you will have two guys here, and then you have to put this edge this way or that way, and then they become comparable. All right? So that's an interesting property because now it gives us some notion of you have these pasts, and there is a notion of length of this interval order based on the number of pasts. Okay? And actually, you can define your function ak by taking any function that will associate to some h, some history h prime, which is smaller, which is of length k, or at most k. Okay, so for instance, what we do is that actually we take this history and we keep precise the last k intervals, and the rest is just collapsed in one. Okay, and this gives us our approximation. So I'll just give you a little example to understand this story of intervals. So here is actually, maybe you are going to ask, so this, there are some edges missing here. But just to have the idea, so actually there is a canonical representation for these interval orders, because now, okay, there is this result saying, okay, you can have this interval orders and you can have this past and all these things, but we are not going actually to manipulate really these pasts. We are going to encode them in some way. And this encoding is based on another interesting result, is that there is a canonical representation for these interval orders using some maps. So actually for each operation, you associate an interval, okay, in the range between 0 to the length of the structure that you have. So, and how do you define this interval? By counting the number of pasts that are before you, strictly, and the number of pasts that are before you or incomparable with you. Because the next guy will be after this to the whole set, okay? So for instance, if you look at this picture, this guy is the first one, as 0, 0. If you take this one, how many people before him? 1, okay? So you have, but this guy is incomparable with him. So I am talking about this guy, right? Pop 1. So you have this guy and those guys, these two guys are incomparable. So it gives you interval 1, 2. Now if you look at, okay, and the rest, now look at this one. He has 1, 2, 3, 4 people incomparable with him. And so he has this interval 1, 4, and so on. So basically you have those guys are like barriers in this order. So you have here 0, 0, and here 5, 5. And then you have this sets here that's define different kind of pasts. Okay, so this is a canonical representation. How do we are going to use it? Actually, we are going to use counters to count how many operations are in each interval. And this gives you the whole information. So you can now take in, your canonical representation. You can define this multiset where for each operation you count, well, actually, you put this element, this pair, the operation and the interval where it occurs. All right. Now, since it's a multiset, you can represent it using counters because you count for each interval how many occurrences for each operation. Right. And now you can show that actually checking that this history of this execution is in this set, if and only if, if you now reduce these things to multisets, you can just check that this multiset is there, or if you want this vector of integers is in this set of vector of integers, if you represent multiset as vector of integers. Now, we have reduced now this story of history inclusion to inclusion between multisets. So the fact that we consider only, k-bounded length histories, so you can now have this a finite number of counters, and you can now track, let's say that you are doing monitoring, okay? So you are looking at your trace. You keep each time, this approximation by keeping precise, the information about the last k intervals, where of course this technically you need some work, but okay, this is what you can do, and you build a monitor, okay, which is going to track this information along the paths. And you have to check each time that what you get is in this representation of the second library. Of course, this now has to be provided, okay? But if you have, let's say, a formula that represents this, so this, you have to check that this vector of integers you have satisfies this formula. And actually what we do is that we provide a logic that allows you to represent these formulas, and we show that checking that an element satisfies this is polynomial. So that's which gives you an efficient checking, and then you reduce your problem, conceptually to an invariant checking. You can do it dynamically, or you can do it also statically. Now, of course, the problem is how do we get these formulas? So, well, what we have done is that you can show that for common data structures like queues, sets, whatever. So these specifications, in some sense, they can be given. You can define them and prove that they are sound and complete. But you can also compute them automatically in some cases. So, but here you have to assume that the number of methods and the number of values that you manipulate is finite. And in that case, you can use what is called the paric image computation in the case where your data structures are bounded and represented in a regular or in a context-free way. Okay? Good. So that's the. I should stop. Yeah. When? How? 4 minutes. Okay. Just to show you some experiments, because now what we have done is that, all right, so this is for the dynamic analysis. We have compared this approach with the standard approach. Let's say the approach that is implemented in lineup, where you look at executions and you try all possible linearizations. So this is the reference here, and this is this white curve here, okay? So we look at up to some number of executions, and we see what is the coverage by this standard one, and we look at what our method give us for increasing number of Ks till 4. What you see is that if the more you have long number executions, so you take executions of in this range, you see that now the coverage of our method becomes somehow almost what the original method do. I mean the standard method do. And even for small bounds, like k is equal to 3, give us everything here, right? So except in some very small cases, well, this one is not clear why there is this peak there, and there is this place here where we miss some bugs. Why? Because actually, when you do this approximation, so maybe this approximation is not buggy, but actually you may find another execution. This is what we hope, is that there is another execution such that the approximation will catch the bug. But now if you do small executions, maybe, and you have a lot of operations, then maybe you have little chance to catch them in this way. So, but this happens only with very small, for when the computations are small. But the more you take, long computation, the more your coverage becomes better. Now, if you look at the overhead, so this is in a logarithmic scale. So this is the overhead introduced by our monitoring, and this is the overhead introduced by the monitoring in the standard approach. And you see that this one somehow remains more or less constant, whereas the other one explodes exponentially. And we have also done experiments with the static analysis, and the interest of this is to show that actually you can reduce this problem to a reachability problem that you can now give to tools like, well, here we have tried CSEC, and this is a tool by Gennaro Parlato, who is based on CBMC, doing bounded context switch analysis. So here we have injected different kind of bugs, and this is the number of push and pops. K, this is our bound, okay? M is the number of, okay, this is how, because this is a parameter for this tool, you have to develop the loops. And this is the number of rounds also. So here it's up to 3, you see, this is the, let's say, the context switches. And you see with these bounds, well, the times are quite reasonable. But the interest here is that you can reduce with this method the reasoning of observational refinement to what the existing tools can do. So, okay, to conclude, so we provided the characterization, a precise characterization of observational refinement that leads also to a bounding concept, which is based on this interval length notion. And we have shown how you can reduce this observational refinement checking to reachability analysis. And what we get is a method that is efficient, both in terms of complexity and number of bounds that are used, and can be used in different contexts. Now, there are many, of course, questions that are still pending. For instance, could be interesting to see if instead of using this counting representation, one can use other approaches based on this interval length bounding. For instance, what we have done is reduction to reachability and using counter to, to encode several computations. One could maybe consider different approaches based on simulation checking, for instance. Also, if one considers special classes of concurrent objects, maybe one can get also more efficient techniques. And of course, another interesting problem is what happens if we have a weak memory model. In that case, what would be, already understanding what does it mean to have linearizability and observational refinement in that case, and what would, again, the decidability complexity result, that's another story. And finally, I mean, what I have shown here is all about concurrent object with shared memory. And another challenge is how to generalize this kind of work to distributed systems. And so we have started looking at distributed replicated data structures, the problem of how to formalize and how to verify eventual consistency, causal consistency, and this kind of concepts, which are weaker than linearizability, because in that case, you know that linearizability cannot be ensured in general. So that's all.
Any questions? Okay. Yeah, I have one question about so this doesn't assume anything about the linearization point, right? To total dynamics. So can you somehow combine it like something, or some method, like for the fact you know what the linearization points are, But for others, like the read-only operation, you may not know, so you have to enumerate them.
I mean, in what we do, actually, we got rid from linearizability completely, because now you reason about observational refinement. And this observational refinement, you can encode it using these counters and all these things. You don't have to consider, anymore this linearization point, because that's actually the source of
complexity, is to find this linearization point and so on. And here you don't reason in terms of linearizability anymore, right? So, but as I said before, you could, I mean, in the case where this linearization point are fixed, well, you can reduce them, but still the problem will be complex. Yeah, because you have to go to this Petri nets or vector addition systems. I mean, this is, of course, will not allow you to prove correct something. That's actually another interesting question, is when you do this approximation schema up to some point, can you check some condition that allows you to say that, well, now since I have checked up to this, and I have checked this condition, I know that it will be true for every k. This is like finding dynamically some cutoff bounds. But
Once proof or certain amount will be correct for all the...
Yeah, but you have you need some
Yes,
test for that.
sure.
Yeah, so it's not clear. Yeah.
Okay, so if no more questions, so the lunch is here, I see. So let's have lunch and then resume it.